Robotics doesn't become advanced when the hardware gets complex. It becomes advanced when decision-making, perception, and localization come together. Car 4 is where students move beyond microcontrollers and into real Linux-powered autonomy. Welcome to ZAS Robotics. Car 4, Raspberry Pi Autonomy Foundations. Car 4 is the fourth robot in the ZAS Navigational Robotics series. After mastering sensors, motion control, and closed-loop autonomy on Car 3, Car 4 takes students into the same foundations used in modern robotics research and industry. This is where robotics shifts from control to understanding the world. At its core, Car 4 is a fully assembled Raspberry Pi-powered navigational robot with two layers, Raspberry Pi layer and a LIDAR layer. Designed for multi-sensor fusion, odometry, computer vision, and SLAM-ready learning. Built on a robust three-wheel chassis and a clean integrated PCB layout, it is built for serious learning and real-world applications. Supports Raspberry Pi 0 2W, Pi 3, Pi 4, Pi 5. It uses high-precision DC 370 encoder motors for accurate motion tracking. At the heart of this robot lies a powerful sensor suite, an MPU 6050 IMU for acceleration and angular velocity, a QMC 5883 digital compass for accurate heading, a Neo 6M GPS module for real-world positioning, a TB6612 motor driver, an OLED display that shows real-time robot feedback.
A Raspberry Pi for real-time control and hardware interfacing.
Dedicated power supply module and 18650 batteries power pack for Raspberry Pi. A second power supply to power encoder motors from 18650 batteries. Comes with a battery chargers. Pi camera for deep learning and computer vision models. An HCSR04 ultrasonic sensor for distance measurement using high-frequency sound waves. LIDAR, T-Mini Plus, A1, C1, X3, and many more in YD LIDAR series. Everything is pre-mounted, calibrated, and engineered, so students focus on algorithms, not wiring errors.
Now we move into deep learning for autonomous navigation. Using Raspberry Pi cameras, our robot runs real-time object detection and scene understanding, identifying obstacles and drivable space. End-to-end neural networks predict steering or generate waypoints, while multi-sensor fusion combines vision with wheel encoders, IMU, and digital compass data for stability and accuracy. All models are optimized and deployed directly on the Raspberry Pi using lightweight, edge AI pipelines, delivering smooth, intelligent, fully on-device autonomy. Within this framework, students can implement imitation learning pipelines, such as behavior cloning, where convolutional neural networks map visual observations to control outputs through fully connected layers. Perception, vision AI, YOLO, Nano, object detection, mobile net, SSD, real-time vision, Deep Lab V3, UNet, semantic segmentation, driving intelligence pilot, net, style, CNN, end-to-end steering, CNN, transformer, waypoint prediction, behavior, cloning, and imitation learning deployment, edge AI, TensorFlow, light, quantized models, INT8, FP16, on-device, no cloud dependency. Beyond perception, this robot learns how to act using reinforcement learning. The car treats navigation as a decision-making problem, observing its environment, choosing actions, and improving through rewards. Policies trained using modern reinforcement learning algorithms learn obstacle avoidance, smooth steering, speed control, and goal-reaching behaviors. Vision, encoders, IMU, and compass data define the state, while motor commands become learned actions. Training begins in simulation and transfers to the real robot using hybrid RL and classical control for safety and stability. The result is adaptive, self-improving autonomy, running fully on device, without predefined paths or rules. Problem formulation, Markov decision process, MDP, state, action, reward, policy, Goal-directed navigation, RL algorithms, Q learning, deep Q networks, DQN, proximal policy optimization, PPO, soft actor critic, S8, TD3, continuous control, learning capabilities, obstacle, avoidance, speed and steering, optimization, recovery from disturbances, long horizon decision-making. Car 4 is vision-ready by design. With monocular or stereo cameras, students explore the foundations of robot perception, including feature detection and description, feature matching and geometric consistency, motion and pose estimation, visual odometry concepts, SLAM-ready pipelines. This is where navigation meets machine perception, the same ideas behind autonomous vehicles and mobile robots. Computer vision techniques. LIDAR transforms a robot from reactive to spatially aware. With LIDAR, students learn how robots perceive geometry, not just obstacles. They work with real laser scan data to detect walls, objects, and free space, and convert raw distance measurements into structured representations of the environment. Students implement 2D mapping and localization, perform scan matching, and build occupancy grid maps used in real autonomous systems. They learn how LIDAR integrates with wheel odometry and inertial sensors to reduce drift and improve accuracy through sensor fusion. Most importantly, LIDAR enables reliable navigation in dynamic environments, forming the foundation for SLAM, path planning, and reinforcement learning-based autonomy. Car 4 prepares students for ROS2 navigation stacks, SLAM systems, AI robotics and reinforcement learning, research projects, and final year theses. It bridges the gap between academic theory and industry-grade robotics systems. Students leave with real skills, not just experiments. Car 4 isn't just another robot. It's a foundation platform where students stop following tutorials and start building autonomy from first principles. This is where robotics becomes real. Visit our website, explore our GitHub, watch tutorials on YouTube, and take your next step into advanced autonomous robotics, starting today. In this advanced robotics journey, you are not alone. You have the support of the strong ZAS Robotics community. Follow us